Ladies and gentlemen, imagine two huge planets crashing into each other, creating a spectacular explosion of cosmic energy. These rare and massive events have shaped the destiny of the universe, leaving a profound impact on the celestial stage. In the grand dance of space, we witness awe-inspiring displays of power that shape the cosmos in extraordinary ways. But, have you ever wondered how planets avoid crashing into each other? How do they navigate their orbits with such precision, seemingly knowing where to turn and where to go? The answer lies in the fundamental laws of physics, particularly the force of gravity. This mysterious force keeps the planets in a delicate balance, harmonizing their forward momentum with the sun's gravitational pull. As we explore the marvels of the universe, we'll delve into the cosmic dance of planets and seek to uncover the secrets of their celestial choreography. Join me on this journey of wonder and discovery into the grandeur of nature's design. Welcome to the unraveling of the cosmic ballet. Why don't planets crash? Let's find out the answer. The reason planets and other celestial bodies don't crash into each other is primarily due to the fundamental principles of physics, particularly gravity and the conservation of angular momentum. Gravity. Gravity is the force of attraction that exists between all objects with mass. It is the force that keeps planets in their orbits around the sun and moons around planets. Gravity pulls objects toward each other, but at the same time, their orbital motion creates a centrifugal force that pulls them outward. When these forces balance each other, objects remain in stable orbits. Conservation of angular momentum. When celestial bodies formed, they acquired a certain amount of angular momentum due to the rotation of the gas and dust from which they originated. This angular momentum is conserved as the bodies collapse under gravity to form planets. As a result, planets continue to rotate and orbit in a stable manner, following their initial motion. Collision avoidance. The vastness of space means that the likelihood of direct collisions between celestial bodies is extremely low. The space between planets is enormous compared to their sizes, so the chances of two planets crossing paths in a way that leads to a collision are incredibly slim. Dynamic equilibrium. The solar system is in a state of dynamic equilibrium, where the gravitational forces between the planets and the sun continuously affect their orbits. These forces are constantly adjusting, leading to stable and predictable orbital paths. The balance observed in the motion of celestial bodies is a result of the natural laws of the universe, not something set or controlled by a conscious entity. The formation and behavior of planets and their motion is a consequence of physical processes and the fundamental laws of physics. While it might seem incredible that such a delicate balance exists, it is important to note that the vastness of space, the enormous timescales involved, and the predictable nature of gravitational interactions make this arrangement sustainable over long periods. In summary, the motions of planets are governed by the laws of physics, particularly gravity and the conservation of angular momentum. These fundamental principles create a stable and orderly solar system without the need for conscious intervention. Is it possible that they can lose their orbit? Yes, it is possible for celestial bodies to lose their orbits or experience significant changes in their orbits over long periods of time due to various factors. These changes can be caused by interactions with other celestial bodies, external gravitational influences, or even internal processes within the body itself. Here are some scenarios where a celestial body could potentially lose its orbit. Gravitational interactions. When planets or other massive bodies come too close to each other, their gravitational interactions can alter their orbits. If a celestial body gets gravitationally influenced by a more massive object, it may be captured into a different orbit, ejected from the solar system, or collide with another body. These interactions are more likely to occur in regions with a high concentration of objects, such as in dense star clusters. Close encounters with stars. Passing near a star can also affect a celestial body's orbit. In some cases, a close encounter can lead to the ejection of a planet or other object from the solar system altogether. Tidal forces. For moons orbiting planets, tidal forces can cause changes in their orbits over time. Tidal forces result from the difference in gravitational attraction between the near and far sides of the Moon, causing it to gradually alter its orbit. Solar radiation. The pressure of solar radiation from the Sun can exert a tiny force on objects in space, known as the Yarkovsky effect. Over time, this effect can cause subtle changes in the orbits of asteroids and other small bodies. Planetary migration. In the early stages of the solar system's formation, some planets might have undergone significant orbital migrations due to interactions with the surrounding disk of gas and dust from which they formed. While these scenarios are theoretically possible and have been studied extensively through computer simulations and theoretical models, they are generally very slow processes, and in the short term, the orbits of planets and most celestial bodies remain relatively stable. Major changes in the solar system structure are considered rare and would typically occur over millions or billions of years. In recorded history and human observation, we have not witnessed any significant changes in the orbits of planets. The stability of the solar system structure is one of the reasons why we can make accurate predictions of celestial events and planetary positions for centuries into the future. It is important to note that our understanding of these processes comes from the study of celestial mechanics, computer simulations, and observations of other planetary systems. As our knowledge and observational capabilities improve, we continue to refine our understanding of the dynamics and long-term stability of the solar system. Why is it that orbital disruptions, which can occur in dense star clusters, do not happen within our solar system? The reason why the orbits in our solar system remain relatively stable, despite the presence of many celestial bodies, is due to the vast size and low density of the solar system compared to a dense star cluster. Several factors contribute to the overall stability of our solar system. Low density. While the solar system contains multiple celestial bodies, planets, moons, asteroids, etc., the space between these objects is vast compared to their sizes. The average distance between planets is quite large, which means the likelihood of direct collisions or close encounters is very low. Dominance of the Sun. The Sun is by far the most massive object in our solar system, containing more than 99% of the total mass. Its gravitational influence dominates the entire system, helping to stabilize the orbits of the planets and maintain the overall structure. Formation and evolution. The solar system formed from a rotating cloud of gas and dust. During the early stages of its formation, interactions between particles in the protoplanetary disk led to the planets forming in relatively stable orbits. The conservation of angular momentum in this process helped to define the orbits of the planets. Stable planetary orbits. The planets in our solar system have been in their current orbits for billions of years. While they might experience slight perturbations due to gravitational interactions with each other, these perturbations are generally small and do not significantly alter their overall orbits. In contrast, dense star clusters have a much higher concentration of stars in a smaller region of space. In such environments, close encounters between stars and other celestial bodies are more frequent. These close encounters can lead to significant disruptions in orbits, gravitational captures, ejections from the cluster, or even collisions. While our solar system is not entirely immune to external influences, the probability of a major disruptive event is extremely low due to the factors mentioned above. The vastness of space, the large distances between celestial bodies, and the dominant influence of the Sun's gravity make the solar system a stable and orderly environment on a human timescale. However, over extremely long periods of time, billions of years, small perturbations can accumulate, leading to long-term changes in the orbits of some bodies. But for practical purposes and human lifetimes, the solar system remains remarkably stable. If you've enjoyed this video and want to stay connected to the fascinating world of astronomy and space exploration, make sure to subscribe to our channel. By subscribing, you'll be part of a community of fellow enthusiasts who share a passion for the wonders of the universe. Don't miss out on the latest updates, informative content, and exciting discoveries. Hit that subscribe button now and join us on this incredible journey.